So we've seen this slide before. We said that anytime we've got a changing magnetic field through a coil of wire, what happens? We end up inducing a current in that loop of wire. We end up inducing a voltage across that loop of wire. We end up with an induced EMF. All right, so there's some voltage that's produced as a result of a changing magnetic field through the area of this coil. And you guys might guess what's coming because we talked about flux and we talked about magnetic field through an area. And we said that flux is magnetic field times area times cosine of that angle between perpendicular to area and magnetic field. So what we're going to do is we're going to come up with a way to actually calculate this induced voltage, this induced EMF. And it's right here. That curly E, that's EMF. That curly E right there is basically, this is voltage, just kind of same thing. I don't know why we call it EMF. We do, fine. So the EMF that's produced by having a coil in a magnetic field where there's some kind of change in the flux is equal to, well, the number of loops of wire in my coil times the change in flux over the change in time. And we remember that what flux is equal to BA cosine phi. So this literally says then that our EMF is equal to, well, however many loops that we have, or turns that we have, I guess if I use the right term, times the change in BA cosine phi over the change in time. All right. So that is a great formula there to figure out EMF or voltage. So, well, it's voltage, right? The SI unit for EMF is voltage. Okay. All right. So let's see what comes next. Probably an example problem. Okay, so we've got a coil of wire here that's wrapped around basically 20 times. And I keep making circular circles. This could be a circle, could be a square, could be, I don't know, some funny shape. Who cares? As long as we don't have to calculate the area, as long as we're given the area, we don't really care what the shape is. But we've got a coil of wire wrapped around 20 times. So N is equal to 20 there. And it says it's got an area of 0.0015 square meters. At least I hope that's square meters. Let me move my face out of my view. Whoa, oh, I just made my face bigger. It's too bad you guys can't see that. All right. I probably prefer you wouldn't. Let's see. It says the magnetic field is perpendicular to the surface. Oh, so if the surface is, let me get my little ring. If my surface is there and magnetic field is perpendicular to the surface, that means that what? That my normal to my surface and my magnetic field are pointed in the exact same direction. Probably better in front of my face. There we go. So phi is equal to 0 degrees. So my angle is equal to 0 degrees. Phi equals 0 degrees. What else are we told here? It says initially the magnetic field is 0.05 Tesla. There's my, there we go. And then 0.1 seconds later, it has increased to, okay, so it has increased to 0.06 Tesla. There's initial and final. And it says that it gives me a time. It says that it took 0.1 seconds to do that, okay? And so what are we supposed to do now? We're supposed to calculate this average EMF. Okay, so that formula that we had actually was a formula for average EMF. That's fine. That's all we're going to be looking for anyway, the entire time we're doing these problems. Why is my head, what's going on here? Oh, I had my view off of my laptop screen, so I thought I was uncentered, but yeah, okay, never mind. All right, so it seems like we've got everything we need here in order to figure out the voltage in this or the EMF that's induced in this coil. Let's see here. All right, there we go. Everything I wrote down. Let's see. EMF is equal to N times change in phi over change in time. All right. Well, what does change in phi look like? Change in phi looks like this bit right there. B final times area times cosine phi minus B initial times area times cosine phi. The area is not changing. The angle between the coil and the magnetic field isn't changing. All right, so it's only the magnetic field that's changing. So as a result, what can we do? We can factor out the A cosine phi and just treat this right there. So we're factoring out the A cosine phi, and now we've just got in parentheses B minus B naught. All right. Plug and chug, and what do we get? We get that our induced voltage there is what? 0.003 volts. 1, 2, 3, yeah, 3 times 10, or 3 millivolts. Okay, so pretty small voltage, but yeah, that's all right. That's the result we get anyway. All right. Let's see, I think this is the last slide on this one, but I will, it's the last slide. I'll talk more about this in a minute.